Looked at the molecular orbital diagram of benzene, we really didn't discuss how you can draw or come up with a molecular orbital diagram in the first place. It turns out that it's quite complicated, and for even simple molecules like benzene, generally we have to use computer models that will predict what the molecular orbital diagram will look like. However, there is a method called the Frost circle method that actually allows us to predict what a molecular orbital diagram will look like for simple compounds like benzene and others. This method is as follows. It starts with drawing the ring of whatever aromatic compound we have with one of its corners down. So you can see here for benzene, one of the corners of the benzene ring is pointing down. That would be as opposed to drawing one of the flat sides down. So this is another way we could potentially draw benzene, and obviously we don't want to do this since instead of a corner we have one of the flat sides of the ring down. After you draw a ring like this, we want to draw the molecular orbital diagram by drawing an orbital at each atom within the ring. So we start with this carbon that is down here. We draw a molecular orbital there. Then we have two more carbons above that. So we draw two more orbitals. Then we have two more carbons. So we draw two more molecular orbitals. And then lastly, we have one last carbon at the top. And so we draw a molecular orbital there. Once we have the molecular orbital diagram, we're going to label the orbitals based on their location according to the midpoint of the molecule. So if we draw the midpoint of the molecule, it cuts across this way. And anything below that midpoint is considered a bonding molecular orbital. So that would be these three molecular orbitals. The three above that midpoint are considered anti-bonding molecular orbitals. And if we happen to have any molecular orbitals in the middle or right at the midpoint, then those are considered non-bonding molecular orbitals. We lastly start to fill electrons from the lowest molecular orbital. So we start here adding 2 electrons. Then we come across 2 degenerate orbitals. So we place an electron here, one more electron here. And then since we have 2 left, we go back to this one and we add a second one on this molecular orbital. We have used up all 6 pi electrons that we started with. Remember, benzene has 6 pi electrons because of the 3 double bonds. Those are the only electrons we care about when it comes to the Frost circle method. And then the last thing we want to determine is whether this compound is aromatic or not based on the Frost circle method. If all of the molecular orbitals that are bonding are filled, then this would be predicted to be an aromatic compound. If we have partially filled bonding orbitals, or we start to add electrons to the anti-bonding orbitals, then we will not have an aromatic compound. Let's look at a few examples involving the Frost circle method of potentially aromatic compounds. So starting with the cyclopentadienyl cation, which has 4 pi electrons. This is the structure. You can see it has 2 pi bonds, so 4 pi electrons. We also have a carbon with an empty p orbital. That's where there's a carbocation. And so there's 0 electrons there, but it does allow the pi cloud to be completed. If we place one of the corners of this ring facing down, we can draw a molecular orbital there. And then we have come across 2 carbons above that. So we add 2 more orbitals. And then lastly, there's 2 more carbons on the top here. So we add 2 more molecular orbitals there. We only have 4 pi electrons, so if we start to fill from the bottom, the most stable molecular orbital, we place 2 electrons there, and then we place one here, and we have ran out of electrons. So notice this compound does not have completely filled bonded molecular orbitals. So the cyclopentadienyl cation is predicted not to be aromatic. As we know from what we learned earlier this chapter, cyclopentadienyl cation is actually anti-aromatic. And it's a very stable compound. It's actually a diradical with 2 unpaired electrons. Cyclobutadiene, which has this structure here, has 4 pi electrons due to the 2 pi bonds. And if we draw one of the corners down, we can draw a molecular orbital diagram from that. So if we add a orbital here, add 2 more here where the midpoint is, making those 2 orbitals non-bonding. And then lastly, we have one more orbital at the top, and that one is anti-bonding. The one down here is bonding. We have 4 pi electrons, so we fill the bottom orbital, and then we have 2 more, so we put one here and one here since these are degenerate orbitals. This compound has partially filled molecular orbitals, so it is not going to be aromatic. In fact, it's predicted to be anti-aromatic, as we learned earlier in this chapter. One last point that I forgot to mention is that notice that these 2 molecular orbitals are actually slightly below the midpoint of this molecule. So if we really draw this ring to scale, the midpoint is just slightly above those 2 carbons, and making these 2 orbitals bonding rather than being at the midpoint where they would be non-bonding like these 2 molecular orbitals. There are 2 well-known examples of carbon-based polymers, which are known as graphite and diamond. Graphite is an infinite network of aromatic polymer sheets of benzenes. So the network has multiple benzene rings that are fused together, and then these sheets will be held together through nonpolar interactions. Diamond, on the other hand, is made up of sp3 carbons that are bonded together. So it is not an aromatic network. And then a third form of carbon was discovered about 1986 called buckyballs. They look like this, essentially a soccer ball. Over the years, several sizes have been discovered. This one here is involving 60 carbons. Buckyballs, despite having only sp2 hybridized carbons, are not really aromatic compounds. The reason for that is due to the non-flat structure that these rings have. So it is completely made up of hexagons as well as pentagons. But despite this, due to the curvature of the molecule overall, the p orbitals and the pi cloud are not able to fully interact, and so that leads to this compound being non-aromatic. Buckyballs are named after an architect that popularized these geodome structures back in the 1950s and 60s. Now, note that buckyballs have been studied since their discovery for many applications, including as a drug delivery system that involves placing drugs inside of the buckyball and then having some sort of attachment on the outside of the buckyball that delivers the drug to a delivery target within the body. Those that worked on the discovery of buckyballs and their applications won the Nobel Prize in Chemistry in 1996.